Hello everyone, my name is Yunsong Zhou from Shanghai Jiaotong University. Today I'm excited to present our work Nexus, Decoupled Diffusion Sparks Adaptive Scene Generation, which has been accepted at ICCV 2025. End-to-end autonomous driving models aim to directly map raw observations and goals to driving controls, replacing the modular stack. Traditionally, these models are trained with supervised learning, imitation learning, or reinforcement learning. But the main goal is to unify perception, planning, and control into a single function. The pipeline typically consists of data collection, training, evaluation, and human monitoring. Once deployed, we need to continuously collect more data, especially for rare but critical failure cases. However, the question is, can we really collect all corner cases in the real world? On average, Tesla FSD drives about 237 miles before a critical disengagement. The challenge is that collecting dangerous corner cases is costly and unsafe. So we ask, can we simulate or generate these critical scenarios instead of waiting for them to occur? This leads to the idea of the world engine. Instead of passively collecting rare failures, we aim to generate valuable corner cases and feed them back into training. The question becomes, how do we generate realistic, safety-critical scenarios at scale? Our work introduces Nexus, a novel generative framework designed to address the challenges of corner case generation. The task is, given the map and historical agent states, generate future trajectories including waypoints, velocities, and dimensions. The key difficulty is balancing reactivity and control. Full-sequence denoising methods achieve goal orientation but are rigid and fail to adapt to dynamic changes. Next token prediction models are reactive but easily lose long-term goals. We need a model that bridges both ends. Our insight is to decouple diffusion noise across tokens. Low-noise tokens carry strong global guidance, preserving long-term control. High-noise tokens adapt flexibly to environmental changes, enabling real-time reactivity. Nexus bridge the gap between reactivity and control, reacting to real-time changes while following predefined goals. So how does it work? Nexus leverages a diffusion transformer where tokens are encoded with both time and denoising steps. They interact with maps and dynamics through attention, while noise scheduling controls how reactive or goal-oriented each token is. This way, the model can remain adaptive while following global objectives. We study different scheduling strategies. Autoregressive and full-sequence scheduling either overfit to local changes or become too rigid. Pyramidal and trapezoidal scheduling achieve the best trade-off, enabling efficient goal propagation while maintaining adaptability. We evaluate Nexus on planning and simulation benchmarks. Results show significant improvements in controllability, interactivity, and kinematics. For example, we observe a 42% error reduction in trajectory planning. This demonstrates Nexus can both follow goals and adapt to dynamic agents. Here we have some visualization of Nexus-generated scenarios. Here we show examples of high-risk scenarios generated by Nexus. An overtaking vehicle cutting in from the right rear. A vehicle merging into the ego lane from behind. An oncoming car merging from the opposite lane. These are valuable training cases that are rare in real-world logs. When combined with rendering, Nexus-generated scenarios become fully realistic training data. This allows us to build a complete R2S2R pipeline, real-world data synthetic corner cases rendered sensor data retraining models. To summarize, we propose Nexus, a decoupled diffusion model for adaptive scenario generation. Nexus bridges reactivity and control, generating diverse, controllable, and realistic driving scenes. It significantly improves planner training and enhances simulation-based validation. Thank you for your attention. I'd be happy to take questions.